Good morning. So today we're going to continue studying graph theory in preparation for the final project. Your exam 2 grades should be posted by tomorrow. It was a longer exam than I anticipated, so it's taken me a bit of time to go through them. So please bear with me on that. Hopefully by tomorrow they'll be up. Okay, so today we're going to continue our study of graph theory. And so let's just go ahead and get started. So graph theory. Okay, so let's start with the definition. Okay, so let U and V be vertices in some graph. Okay, so then a UV path is a sequence of vertices, say U equal to, I'll say UW path, the UW path is a sequence of vertices. U equals to V1, comma, V1, V2, comma, V2, comma, dot, 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 comma, VK minus 1, comma, VK minus 1, VK, comma, VK, and this is equal to W. So here, so let's say where VI comma VI plus 1 is an edge in the graph, and VI appears only once in this sequence. Okay, so it's a technical sounding definition, but it's really not so bad. So a UV path. So let's look at an example to get our heads around this. So suppose that G is some graph, let's say okay, so take a moment to draw that with me. All right, so I'll label these vertices maybe A, B, C, D, E, F, little g, and then maybe H, and then I. Okay. So here we have some graph, and then I'll say that AG path is A comma AC comma C comma CI comma I comma IG comma G. So that's one AG path. Okay. One AG path is that. Okay, so if we look at the graph here, we have A, and then AC to C, and then CI to I, and then IG to G. Okay. Now, does this satisfy the definition? Well, notice that if you look at the vertices in the path, so these are the vertices, A, C, I, and G. So each of those only appears once in this sequence, and the edges there exist in the graph, like AC, CI, IG. Okay. Now, if we looked at this, it would look like this. So here's A, C, I, and G. So basically, a UV path, or in this case, an AG path, is a sequence of vertices and edges that you can traverse through to get from one vertex to the other. Okay? So here, we have a vertex, edge, vertex, edge, vertex, edge that gets you from A to G. That's a AG path. Okay? So, is that definition clear?
Yes.
Yes.
Okay. So we got some yeses here. All right. All right. So I should say, okay, let's continue this definition. So a cycle is a UW path with the addition of the edge UW provided UW is not in the original path. Okay, so let me just kind of redraw this. C. Okay, so there's G. Okay, so a cycle in this graph would be something like, you could take a CD path, and then you can close it off like that. Okay, so then if you drew this cycle, it would look like this. C, I, F, E, and D. So that's a cycle. Okay? So far, so good? In fact, I should probably go ahead and give you some interesting families of graphs. So, is the cycle somewhat clear? It's a path, like a line of vertices and edges where you loop back around at the end.
Yeah, it's clear.
Okay. Okay. Okay, so I have a definition. So a graph is connected if for all u and w that are vertices in the graph, there exists a u-w path. Otherwise, so a graph G is connected. So otherwise, G is called disconnected. Okay. Okay, so let's look at some examples here. So I'll count this graph G over here. So G will be inside of here. Say A, B, C, D, E, F, G, and H. And then I'll call this graph over here, I'll call this graph H. And I'll call this A, B, C, D, E, and F. Okay, so so I just got a question asking, why did I choose these specific points? I just am kind of making up these graphs, and I'm just picking random vertices in the graph to kind of illustrate the definition. And so one of these graphs is connected, one of these graphs is disconnected. Which of these graphs is connected?
The one on the right?
Graph H.
So H. Right, so H is connected. Because if you pick any two vertices in that graph, there's going to exist a path between them, right? So why is G disconnected? I give an example of why it's disconnected. There is no what?
There is no edge between I don't know how to say it.
Well, so look at the definition of being connected. If there's a path, right, between any two vertices. So if you look at G, give me an example that's where there's a path that's missing. So a path can be a sequence of edges and vertices, or just this graph here, for example, there is no AE path. You can get from A to C, A to F, A to B, but no matter how you try to traverse along edges and vertices, you cannot get from A to E. So there is no AE path. So this tells me that G is disconnected. And when you draw it, you can draw it in a different way that might work a bit easier. So for example, this graph G can be drawn like this. This is also G. That's the same graph. And this is B, F, C, A. And then we have E, H, G, D. And the relational structure, the set structure, because you have to remember that graphs are sets. They're not drawn. We just happen to be able to draw them to get an idea of the relation between the vertices in the set. But graphs are an edge set and a vertex set. The vertex and edge set here is the same as the vertex and edge set there, so it's the same graph. It's just drawn differently. And here, you can see that there's like two pieces, right? So being connected is one way of saying is that if you draw it, it's going to consist of like one piece. And it's disconnected if it consists of two or more pieces.
Professor?
Yes.
If for the path, can the vertices repeat by chance?
No.
No. Oh, so it can only be used once.
Right. And that was if you look back to the definition that I wrote down, every vertex appears exactly once in the sequence.
Could you show that with graph H? Because I'm trying to visualize how we can make a path using vertices only once.
Well, just pick any. So pick any two vertices in the graph.
Okay, so D and C.
D and C. Okay. So we just need to find a path from D to C. So here's D. We can go down this edge here.
Yes.
A, and we can go down this edge to B, and we go up this edge back to C. And that would be a DC path.
Okay. Oh, so it doesn't have to use up all the vertices. You just have to find the shortest. Okay, that's my question. But thank you, sir.
You don't have to necessarily find the shortest one either. You could go from D to A to B to E to B. And that's another DC path.
Could you show us an example of using graph H where you find a path using all the vertices?
You can't.
You can't. Okay.
Actually, no, you can. You can. D, A, B, E, C, F.
But you didn't include the edge C, B. Doesn't have to include that or no?
No.
Okay.
That is what's called an Eulerian path, where you use up all the edges in the graph, but you can't do that for this.
Okay. Thank you, sir.
Okay, so a graph is connected if there exists a path between any two vertices in the graph. Okay? It's disconnected if for some pair of vertices in the graph, there isn't a path between them. So for G, I just said, no, there is no AE path, so it can't be connected. Okay. Okay, so connected, disconnected, very important for the final project, okay? Okay, so I'm going to draw a bunch of graphs. So okay. And take me a minute to do this. And then maybe like okay. So here we have a collection of graphs. Now, there are several of these on here that are kind of different than the others. So let me give them labels. So I'll say like this is A, B, C, D, E, F, G, H, I, K. So let's say, so 5 of these graphs are similar. Can you group 5 graphs here that all kind of you think have something in common? You can do this in a lot of different ways, by the way. It's kind of an arbitrary question, but I'm giving you a hint that 5, though, belong to the same like big class of graphs. So which 5 do you think belong to the same family, meaning that they're a part of a set of graphs that all have something similar in common?
A, F, C, D, and H.
Yes. A, F, C, D, and H. Why are those similar?
There are no cycles.
Right. Exactly. Notice that all the other graphs outside of this collection contain some cycle somewhere, right? Like here, E has a cycle right there, K has cycles all over the place, I has cycles everywhere, G has cycles everywhere. But these graphs here don't have cycles. Can anyone guess the name of these graphs? They belong to like a big family of graphs, and these graphs are called, take a guess. It literally is just a guess. These are trees. So trees are graphs that do not contain cycles as subgraphs. And I'll write down this formally in a moment, but I like starting it out by giving you pictures to kind of see it before writing the formal definition. Okay, now 3 of these graphs belong to the same class. I wonder if anyone can guess which 3 I'm thinking of that belong all to the same family.
G, I, and K.
They do, but that's not the 3 I'm looking for. By the way, so I'm curious, why did you say G, I, and K?
Something about K, like K4, K5, but K is not, K is actually not a K, or is
Right.
it?
It's not.
It's not, no.
It's just I just gave a letter to denote it.
Okay.
What about, I'll tell you, there's another collection. I, K, and E. What do those have in common? They all share something in common. And it involves one of the definitions that I went over in a previous lecture. I'll give you a hint, degree, vertex degree.
For, I guess, each vertex has a degree of 3
Right.
in the graphs.
In each of these graphs here, every vertex has degree 3. These are called 3 regular graphs, also called cubic graphs, because every vertex in the graph has degree 3. Now, if I look at the inclusion of G in there, G, I, K, E, those would all be regular graphs, because every vertex has the same degree. Right? Every vertex over here has degree 4, every vertex has degree 3. They all have the same degree and they're called just regular. But if there's a specific degree like these, then it's that degree regular. So these are 3 regular. That would be a 4 regular graph. Okay. Okay, so this is kind of just talking about some like the major families. And families are sets of graphs that all share something in common. So like trees consist of all graphs that don't contain cycles as a subgraph. 3 regular graphs are all graphs that have, where every vertex has degree 3. Regular graphs are graphs where every vertex has the same degree. So let's look at some other families. Okay. All right, so I'm not gonna have enough room, I don't think. So this is one family. And they're denoted by K subscript N. Can someone tell me what the subscript is denoting?
Vertices.
The number of vertices or the order of the graph. And what do all these graphs have in common? I'll go ahead and draw case 6 just so you can see it. This would be case 6.
Every vertice is connected by an edge to every other vertice. Or wait, no.
Correct.
Yeah. Okay.
But you should say vertex when using single.
Oh, right.
Vertex. So basically, what you can see is that every vertex in the graph is adjacent to every other vertex in the graph, and these are called complete graphs. So they're called complete graphs because they have the maximum number of edges possible in a simple graph. Like for example, we look at K3 here. We cannot add another edge without getting a loop, or not a loop, a multi-edge. And simple graphs have no multi-edges. So if I try to add an edge between any two vertices in there, I get a multi-edge, which that breaks being a simple graph. Same thing with K4, K5, every complete graph. If you try to add an edge, you'll get a multi-edge, so we're avoiding this. Okay, so let's look at some other ones. You should be able to guess these. So what do you think these are called? P sub n. You can definitely guess these.
I mean, aren't they paths where?
Yeah, these are just path graphs. Okay, so what about these? What do you think these are called? So C subscript n. What are those?
Cycle graphs?
Yeah. These are cycle graphs. Okay, so I want as many people to participate as possible because this is going to get rather entertaining rather quickly now. So I'm going to keep on doing this, and the name of the game is to try to guess the name of the family. Okay, so what do you think those graphs are called? Take a guess. There is no wrong answer.
A tree graph? I mean,
well, those are trees, but they have a specific type of structure. Like in particular, what does the second number denote?
it denotes the number of vertices that the central vertex connects to.
Right. And so, by the way, when you're looking at trees, these are the degree 1 vertices. Those are called leaves. So these are the leaves of that tree. So the second number is the number of leaves. But not thinking about trees for now, just what do you think a good name for those graphs would be? Take any guess you want. Clearly, these are star graphs. Right? Maybe they kind of look like stars. All right, so let's keep on going. Get some other families of graphs. So what about these? This name isn't as it's not as fun to me, but it's kind of related. So these are denoted by S, X, Y. What do you think those are called? Things that look like that. They kind of look like stars, right? So the name is close. I'll just tell you because I doubt you'll guess this one. These are called double stars. And these are also trees. Can you guess like what the numbers X and Y mean?
The number of connected vertices on the left and to the right.
You're getting, that's the right idea. It's the number of leaves on the left and the number of leaves on the right. Okay, so let's keep on going. So a lot of times you can build a family of graphs by starting with one of the simple families that I mentioned and then kind of like doing something to them to make them different. So what do you think these are called? So if you start with a cycle and then you add a leaf to each vertex in the cycle, you get these graphs. So start with a cycle, and then you add a leaf to each vertex on that cycle. What do you think those are called? Take a guess.
A double cycle.
Starfish.
These are called
Polygon
sun
tree.
graphs. Right? Okay. So another type of graph that you can form in a similar process is if you start with a path and then you just put leaves on the path like that. So that's one. This is one. And you can do that any number of ways. You just start with a path and put leaves on each vertex of the path. And you can put multiple leaves on a given vertex. What do you think those are called? Take a wild guess.
Caterpillar.
They are. Those are caterpillars. These are caterpillar graphs. If you start with a caterpillar and then you put leaves on the leaves of the caterpillar, what do you think those are called? And you can do that in any number of ways. But what do you think happens when you start with a caterpillar and you put leaves on those leaves?
Butterfly.
No, these are lobsters. These are also trees, right? They contain no cycle. Okay. So there are infinite families of graphs that you can make by doing this construction. And a lot of the times these named families, if it has a name, it's probably because it's important to something, right? It appeared in some academic paper and it happened to be special for some equation or inequality or something. Yeah, that's how they get their names. I've come up with a few myself. The first family of graphs that I ever made for an academic paper look like this. So these all belong to the same family. You don't even know what these are. I'm just illustrating that if you can notice a pattern, you can just build bigger and bigger of the same family. And I'm assuming that you can see how the next one will look. Instead of having, so the first one starts with 1, 2 of these pieces, 3 of these pieces, 4, so forth and so on, and that's how you would connect them. There's just, I find it interesting. Oh yeah, so now let's get back to some definitions. Okay, so H is called a subgraph of G if the vertex set of H is a subset of the vertex set of G, and the edge set of H is a subset of the edge set of G. H is called a spanning subgraph if H is a subgraph of G, a spanning subgraph of G, if H is a subgraph of G, and the vertex set of H is equal to the vertex set of G. Okay. So subgraph and spanning. Okay. So if we look at an example, suppose G is the graph. Okay. Given here, then and that's H. That H is a subgraph of G. Okay. Is H spanning? Anybody? So it is a subgraph, but is it a spanning subgraph?
No, it's not.
No. Right? It's not, because the vertex set of H does not equal the vertex set of G. A spanning subgraph would be something like, let's draw it again. A spanning subgraph would be like, so that would look like this. So that's one such spanning subgraph of G. Okay. Is that definition somewhat clear now? We have subgraphs and then we have spanning subgraphs.
Yeah.
Okay. Okay, so now that we know what a subgraph is, it's just a collection of vertices and edges that are contained in the. Oh, I should probably say something that this is also a spanning subgraph. The vertex set of H equals the vertex set of the graph. So this just happens to be a spanning subgraph that isn't connected, which is fine. It still satisfies the definition of being a spanning subgraph, so it works.
So it's a subgraph as long as the vertices are all included within both graphs.
What do you mean by all included?
As in, if we have the vertexes, say if we have 10 vertexes in graph G, and vertex H has those same 10 vertexes,
Vertices, plural.
vertices, then can we say at that point that they are spanning subgraphs or no?
H is a spanning subgraph as long as it contains every vertex in the original graph.
Okay, but that's just the vertices, not the edges. So the edges could be whatever.
The edges you don't have to include.
Okay.
Mm-hmm.
Thank you.
You can leave out edges and just have like one spanning subgraph is just to take all the vertices with no edges. That's like one spanning subgraph. All the vertices with no edges. It's spanning, it just doesn't have any edges.
Okay, thank you.
Mm-hmm. Okay. And now we can finally define what a tree is. Okay. So a graph G is a tree if it contains no cycle as a subgraph. Okay, so that's what it means to be a tree. And we already saw a bunch of pictures of these. It looks like this. And they can be all kinds of complicated looking things. Just as long as it doesn't have any cycles, it's a tree. Okay. Does this make sense? Like the definition of a tree?
Yes.
Okay. Okay. So simple definition, we have some examples here. Okay. Okay, another definition. So let G be a connected graph. Oh, in the definition of a tree. I shouldn't have. So in the definition, it should say a connected graph G is a tree. If it contains, so in the definition I just erased, very, very, very important. The graph has to be connected to be called a tree. So because the graph is a tree, if it contains no cycles. That's important. Can you guess what? So, what do you think this is called? Like if this is your graph, what type of graph do you think that's called? All of that together is one graph. Does it contain any cycles? No, there's no cycles anywhere. What do you think this is called? That's a tree, that's a tree, that's a tree. There's no cycles. What do you think it's called?
Forest.
It's a forest. So a disconnected graph that contains no cycles is called a forest. So in order for it to be a tree, it has to be connected. It's disconnected and contains no cycles, it's a forest. Otherwise, it's a tree. Okay. So next definition, let G be a connected graph. An edge E is called a cut edge of G if the graph obtained by removing E from G and this is typically denoted by G minus E. So if the graph obtained by removing E from G is disconnected. So this is the definition of a cut edge. It cuts the graph into two pieces, in other words. So so A, B, C, D. Instead of saying E up here, I'm just going to say UW, because every edge is a pair of vertices. So if this is your graph G, what is a cut edge in that graph? There's one.
DE.
DE. DE is a cut edge. Right, because if this is G, and you look at G minus the edge DE, it'll look like this. This is G minus DE, and that's G. You see that? If you just remove that edge, you now have two different pieces of the graph. E, H, I. So that would be a cut edge. Okay.
Cool.
So are cut edges kind of clear?
Yeah.
All right, so if you know what it means to be connected, there's a path between any two vertices. A cut edge is basically an edge that disrupts some path between two vertices. Right? Okay, so let's keep that in mind and prove a little proposition. But we haven't really proved anything, we've just been kind of looking at definitions. Let's prove a little proposition. And this says that every edge in a non-trivial tree is a cut edge. So non-trivial, so the trivial graph is this. That's the trivial graph. It's the graph with one vertex and no edges. So, and that is a tree, there's no cycle. So we have to like, and it has no edges. So we just exclude that and we say, okay, the proposition says every edge in a non-trivial tree, so every tree that's not that, so every edge in these things is a cut edge. So like, how would you even prove something like this? These like, everything that we've been dealing with in graph theory deals with some type of definition. There's not really any numerical properties associated besides maybe like degrees and order and size, but this might seem kind of weird. So if you look at this, you're like, okay, let's like, graph theory is perfect for drawing pictures, right? So suppose that we have a tree T, it's in here somewhere, right? Okay, and suppose that by contradiction, maybe. So suppose that, so contradiction. This is like my scratch word. So maybe UW in the edge set of T. Let's assume that that's not a cut edge. And again, it's scratch work, so I'm just going to put not a cut. Okay? So then, okay, here's U, and here's V, or W. Okay? And they're in the tree T. So if it's not a cut edge, can someone tell me what that means for it not to be a cut edge? But what does it mean if it is a cut edge? So if it is a cut edge, what's the definition? It means that if you remove the edge, the graph is disconnected, right? And that's the definition of being a cut edge. Make sense? Yeah.
I guess if it's not a cut edge, then I guess there's more than one edge that connects that vertex.
Well, generally speaking, if you look at the definition, it's not a cut edge. So maybe like here's T, and here's U and W, and here's T minus E over here, and here's U and W. And like these things could be connected to whatever, doesn't matter. If it's not a cut edge, then this must be connected. Right? If it's not a cut edge and we remove it, then the graph is still connected. Right?
Yes.
So if it's not, then we can remove it and this thing here is still connected. But in particular, if T minus E is still connected, there is a UW path, right? in T minus UW. Right? Because if it's connected, then there's a path between any two vertices in the graph. So in particular, in T minus UW, I'm sorry, there has to be a path somewhere that gets from W to U, right? And this UV path is in blue. If it's connected, there is some way to start at W and walk along vertices and edges and get back at U, if it's connected. But then, if we look at that path in T, what happens? Why is that bad? Right there. By the way, what is T? T is a tree. Right, so we didn't know that that path existed. We just know that UV is an edge in the graph. And we assume by contradiction that it's not a cut edge. So then we remove it, and we see that, oh, since it wasn't a cut edge, this graph is still connected. So that means that there is a path, a UW path, in this piece over here, just after we remove that edge. But if that's there in this graph, it's also in the graph before we deleted the edge. But what does that make right there?
Doesn't that make
A
a cycle?
That's a cycle, right? If there's an edge between U and W, and there's also a path that doesn't use that edge, that together makes a cycle. But that's a contradiction, because T was a tree, and T didn't contain any
Wow.
cycles. So this is like kind of the scratch work. Now I'm going to write it out a little bit more formally, and I'll draw a picture along the way so that you can see it. Okay, so let T be a non-trivial tree and by way of contradiction, suppose the edge UW in the edge set of T is not a cut edge. Okay? So then we could say, by definition, if it's not a cut edge, we remove it, and it's still connected. So by definition, T minus UV or UW is connected. So I'll put the picture over here. So here's T. Okay. And then here's U, here's W. And then over here, this is T minus UW. So I got rid, I cut that edge away. Okay. So since T minus UW is connected, right? There must be a UW path in that graph. So there exists some UW path in T minus UW. And I'll call it P. Okay. Okay. So that path P is here. And we don't know where it goes, but it definitely connects U and W over here. This is P. Okay. Now, no edges in this P, no vertices and edges in that P were deleted from T to UW. Right? So notice in particular, P is a path in T. Right? Because we didn't add anything to T, we only got rid of that edge. So everything along this path here better also be in the previous graph, right? So here's P again. Here's P. So should say this, P is also a UW path in T. But P didn't use the edge UW because that edge is deleted over there, right? This is a contradiction. Since P union the edge UW is a cycle in T, and T was a tree. Contradiction. So that edge must have been a cut edge, since otherwise we can form a cycle. Okay.
Cool.
Now that I've written it out, you wouldn't have to replicate this on your own or anything, but do you at least like understand why, like, do you understand the proof?
Yeah.
Okay?
Yes.
And again, I like the pictures, right? Like, so it pops out immediately. Like if we assume that that's not a cut edge, right? Then immediately when we remove it, there has to be a path between U and W that doesn't use that edge, right? But then if we look back at the original graph, that path didn't use that edge UW. So if we connect it, we form a cycle, which is impossible. So it most definitely must have been a cut edge, since otherwise we get this, we can literally construct a cycle in the original graph. Okay. Okay. So this is related to what we're going to do for the final project. And I'm going to go ahead, because we're running out of time, I'm going to mention what you're going to do for the final project. So you can go ahead and get a head start. Okay, so final project. So up to 5 members. Or less. And you're going to use Python to program from scratch trims algorithm for the minimum weight spanning tree problem. Okay, this is also referred to as the MST. So after reviewing today's lecture, I opened up the homework to be due next Sunday. So there's an extension on the homework. So after you caught up on the homework, review today's lecture, I would get on YouTube and just start looking up the minimum spanning tree problem. And then tomorrow morning, I'm going to post another video that will probably cover it. And then on Wednesday in class, I'm going to talk to you about putting together the structure of your program to implement it in that, so that it looks like a professional-ish Python package. Okay. So also find your members. Okay. Find your members.
Professor,
Yes.
do we have to, I guess, notify you as to who is part of a group? Like, do we send you an email regarding our names and like?
Not yet.
Not yet.
By Wednesday afternoon, yes, though.
Okay.
So
do we each have to email you, or could one person just send you an email?
one person can send me an email with a list of all names in your group.
Okay.
Okay, and you can even work with students. Yeah, I think 5 is the most I would do.
Okay. Thank you.
Mm-hmm. So maybe for your members, I would say maybe a few of you, if you're able to put this project on GitHub, that's like a 10 bonus points on the then I put the grade in. So if you don't know what GitHub is, have one of your members or all of you look it up. Each of you is going to have to make an account if you want the full bonus points. You make a GitHub account, and that's where you'll store your projects so that you can work remotely and send versions to each other. Yes, you can have a member from another class, but just don't exceed 5 members per group. So your members don't have to come from Monday, Wednesday, or Tuesday, Thursday. It can be a mix, just so long as there's not more than 5 members. Okay. But definitely try to get GitHub involved. This is important for every single one of you. All of you are CS majors or data science majors or statistics or math. If you're doing any type of programming, GitHub is what you use in practice when you're out in the real world. Okay? Okay, so I need to render this video and post it to YouTube for my other classes. So I'm going to go ahead and call it a day. Email me if you have any questions, and also check YouTube tomorrow morning.
Thank you.
Have a good day.
You too.